Gosh, I just can't win these days. There goes another week of progress down the drain. I'm so tired of my plants not growing to their full potential.
Well, Lauren, don't you know organic chemists work together to develop fertilizers to help plants grow? I have a friend that is an organic chemist. Meet Alex.
Hi Lauren, I'm Alex. Let me teach you a bit about fertilizers to see what we can do to help you solve your issue.
Okay, first let's talk about what we know about fertilizers. So I'll let you know a little bit about the history of fertilizers. First, superphosphate was made in the early 19th century by treating bones with sulfuric acid. And then they replaced the bones with coprolites, which is actually fossilized feces, and phosphate rock as the phosphorus source. And then the potassium fertilizer industry started in Germany in 1861. And then moving on in the 20th century, the Nobel Prize winning chemist Carl Bosch and Fritz Haber developed the Haber process. So this utilizes molecular nitrogen and methane gas in an economically sustainable synthesis of ammonia, and the ammonia produced in the Haber process is the main raw material for the Ostwald process. And then I'll talk a little bit about what are fertilizers in general. So usually the regular soil lacks the nutrients for plants to reproduce and grow fully. So the nutrients that they're lacking is nitrogen, phosphorus, potassium, calcium, magnesium, and sulfur. But most of the fertilizers these days contain nitrogen, phosphorus, and potassium. Fertilizer is very expensive and can harm the environment if it isn't used correctly. So a farmer like myself, I usually will send off a soil sample to a laboratory, and then they'll do some baseline testing to let me know what kind of fertilizer I should be utilizing. And then by testing the soil, the farmers know. I would know which nutrients and how much to apply to the soil. That way I'm not using too much and making it acidic when it doesn't need to be, or I'm not adding enough. So there's two different kinds of fertilizers. There's organic and then there's inorganic. And the definition of organic and fertilizer sense is a little bit different than what we're used to in organic chemistry class. What they mean by organic fertilizers is that it's plant or animal based. So they'll use manure or compost or slurry in those sense. And then for inorganic fertilizers, this is where it involves more organic chemistry to make them because they're artificially manufactured. But both of them, organic and inorganic, are equally able to affect plant growth.
So fertilizers affect plant growth by supplying nutrients vital to plant development processes. So a main ingredient found in fertilizers is nitrogen, and nitrogen is utilized for synthesizing plant proteins, which leads to stronger stems, more and bigger leaves, and greater crop yields. So nitrogen in the soil is taken up by plants in the form of ions by active transport. So these nitrogen ions are usually in the form of ammonium and nitrate. And fertilizers are important because they supplement the nutrients that the soil is sometimes lacking, and they allow crops to produce more in less than favorable soil environments.
Like mine.
Phosphorus is another main ingredient in fertilizer, and it's used for photosynthesis, storage, energy transport, respiration, and DNA synthesis. But when using fertilizers, it's important to consider the environmental effects. So in order to cater to the high global demand of food, farmers tend to use excess of fertilizers in their crops. And using too much of these fertilizers can alter the fertility of the soil by increasing the acid levels and killing essential bacteria and fungi that are able to naturally produce organic material. Chemical fertilizers are high in nitrogen salts, and when nitrogen is absorbed by soil too quickly, it can cause the plant to become dehydrated, making it more susceptible to pests and diseases. Another issue with using chemical fertilizers is the pollution of bodies of water. This can cause eutrophication to occur, which is the excessive richness of nutrients found in groundwater. This happens when nitrates and phosphates found in fertilizers run off into bodies of water and disrupt aquatic ecosystems by causing the growth of algae that deplete the oxygen in the water. This leads to a toxic environment and leads to the death of fish and other aquatic life. Similarly, fertilizers can cause adverse health effects in humans like cancer and chronic diseases.
Well, cool. I think we know a bit about fertilizers, but we definitely have more to learn. Let's see what the chemists have to say about this.
The Haber process is an industrial process that produces ammonia. It follows this reaction equation here. N2 plus 3H2 converts to 2NH3. The Haber process is reversible and exothermic, and considering the reactants in the equation, it takes N2 from air and hydrogen from natural gas. In the above photo here, the photo is showing the issue that Haber came into contact with. In equilibrium, which is this reaction is in equilibrium, it's a very tough reaction to get started because you must heat it to 400 degrees Celsius and compress to 200 atm and be under presence of an iron catalyst in order to get the nitrogen-nitrogen triple bond to break. Because of this tough starting point, the reaction is in disfavored equilibrium. You have to use a lot of nitrogen and hydrogen just to get a very small amount of NH2 gas. The system is constantly producing ammonia, but a lot of it is reconsumed in the reverse process. Even though the system is constantly producing ammonia, there's never a large yield of it. Because of this issue that occurred, he created the Haber process, which is the bottom equation. In the bottom, the trick to producing a large amount of ammonia is condensing and collecting the product, because this prevents it from going back to the starting materials. Instead of it's no longer in the reaction, it's being completely removed from the system. The system is constantly trying to reach equilibrium, but it can no longer get there because we have removed the products. So Leigh-Chatelier's principle favors the products, so you don't need as much reactants, which in turn reduces cost of the reaction while still producing a reasonable yield. The Haber process makes ammonia, which is used to make many nitrogen fertilizers, an example being urea, which we will talk about next. Urea is a type of nitrogen fertilizer that can be produced in humans, but it can also be synthetically manufactured using anhydrous ammonia. Once urea is placed on soil, a chemical reaction occurs that turns the urea to ammonium bicarbonate, which converts to a gas. If the gas is not protected correctly by the soil, it can easily escape, which is why fertilizer is usually plowed into the soil. Urea is very beneficial for plants that need acidic soil, such as corn, strawberries, and blueberries.
Okay, now we're going to look at an IR spectrum for urea. So we have peaks down here at 1630 and 1690, and that shows amide groups. Also, the peaks at 3300 and 3400 show the NH2 groups for urea. For the mass spectrum, the M+ is at 60. That also correlates to the molecular weight of urea. After the M+, there's a small peak at 61, which shows the isotope for urea. For the NMR graph, there's only one peak, and it's at 5.6. This chemical shift shows the R2NH group. Also, this molecule at the bottom shows that all of the H's are the same, which is why only one peak shows up on the graph. For CNMR, there's a single peak at 160. This chemical shift correlates to the carbonyl group that's attached to NH2s. Now, let's look at the mechanism for urea. First, we're going to start with a cyanate ion and an ammonium ion. The lone pair of electrons of the nitrogen reach out and grab the fourth hydrogen of the ammonium ion, forming ammonium cyanate. Then the ammonia that was just created comes and attacks the carbon here, pushing a pair of electrons onto the nitrogen. After that, we lose a proton, pushing the electrons onto this nitrogen and making it neutral. Once that's done, this double bond here comes out and grabs a hydrogen, and then this extra pair of electrons on the O forms a carbonyl, making urea.
Wow, look at my plant now. Those fertilizers really worked. I even had to repot it.
Bazinga! Sweet plant! Glad I could help.
That was our presentation on fertilizers for organic chemistry at Purdue University. Thanks for watching.